The second example we're going to look at could be something actually similar in terms of the setup of the first example. But so in this case, we have a ball of mass m. It's moving to the right with an initial velocity v. Sounds the same as the last one, except for it collides in an inelastic collision. So if you remember from our description, the inelastic collision is where momentum is being conserved, energy isn't being conserved, so there's some energy loss, but the balls will not still stick together and travel together. They will still separate. So for the case and purpose of how we're going to solve these in terms of just momentum, it's exactly the same as the first type or the first example. But anyway, so it collides with ball B, which is traveling at a, in this case, B is actually moving, so it's not stationary. B is traveling at a speed half that of A and in the same direction. After the balls collide, ball A travels in an opposite direction with the same initial speed, and ball B travels in the same direction with the velocity v, twice its initial speed. Okay, so if it were half v, it's now traveling v. Got it. What is the mass of ball B with respect to ball A? So answering or solving for the same thing, some different setups. The equation we're going to use is going to be the exact same, just some of our initial conditions are different. I'm going to use our same image that we did before, but I'm going to change one thing. B is also going to have a velocity. It's the same direction, but it's half of the speed. So those are their initial velocities. The same setup and equation fits before. The momentum before, or the initial momentum before, should equal the momentum after. And it's just going to be the sum of their initial momentums, right? So the momentum of A we know to be the mass of A, the initial velocity of A, plus the momentum of B, the initial velocity of B, this time is not 0. That's going to equal the mass of A, the final velocity of A, plus the mass of B, the final velocity of B. All right, so we are writing momentum, or not momentum, mass A is m, and velocity, the initial velocity of A is just v. So this is going to be mv. Plus, we're going to keep this as mb because we don't know the mass of B. But we do know the initial velocity of B with respect to just v, our velocity. It's 1/2 v. This is then going to equal mass of A is m. The final velocity of A, it tells us, hang on, the ball A travels in the opposite direction with the same initial speed. Okay, so this is just going to be negative v plus mb, which again, we still don't know. The final velocity of B, it says ball B travels in the same direction with velocity v, so twice its initial. If it was 1/2 before, now it's just 1. So v. Let's clean this up and simplify a bit. mv plus 1/2 mbv is going to equal negative mv plus mbv. And let's move like terms to like. So let's get the mass of B to one side and just m, aka the mass of A, to the other side. So I'm going to add this to the left side. So it's going to give me 2 mv. I can do that because they're like terms. I'm going to subtract this to the right side. Again, like terms, I'm basically thinking this could be thought of as 2/2. I'm subtracting 1/2 from it, so that's just going to give me 1/2 mbv. Both terms have v's, so I can cancel those. I can multiply the 2 to the other side, and I get 4m is equal to the mass of the ball B. So ball B's mass has to be 4 times that of A's in order for this type of inelastic collision to occur.